everyone, welcome to BCP Med. In this video, I want to go over the basics of London dispersion forces. We're going to talk about the probabilistic nature of electron density around the atom and how that leads to transient dipole moments. Let's go ahead and get started. When we talk about electrons orbiting an atom, it's important to remember that they are not anything like planets orbiting the sun. Electrons are quantum particles, which means that they do not have a definite position and instead have wave-like qualities. They have an amplitude that is dispersed throughout the range of the entire atom. For example, if we were to look at what is known as the probability distribution for the 1s orbital, we would see something that looks like this graph. The y-axis tells us the probability of observing the electron at a given distance from the nucleus. The peak corresponds to the average orbital radius of the electron. It's really important to understand it's not like the electron is moving really fast between all these different positions, but rather the matter-energy wave that actually is the electron is distributed throughout this entire region of the graph. Now, from a more practical or observational point of view, we would see the following. If we observe the atom at one instant, the electron would appear to be localized at one position. And at the next moment, it could be in the following position. And then at the next moment, its third position. The point being, the electron could appear absolutely randomly at any point within the probability distribution from 1 second to the next. However, it's not like the electron is moving from there to there to there very quickly. It just is. It's always there, and when we observe it, the wave function collapses such that the electron is localized in this one position at the instant of observation. This probabilistic quantum nature of the electron is important for molecules because multi-electron systems are also probabilistic. Not just a single electron, but the entire electron cloud can shift its position from observation to observation in a completely random fashion. And I want to clarify, observation doesn't literally mean looking at the electron. It's far too small for that, even for the most powerful light microscopes. Instead, observation means interaction with some other atomic level structure, like another molecule or some sort of electronic detector. Going back to the electron cloud, typically, we expect that the electrons will show up where they are most likely to be found, around the peak of that probability graph, which would give a somewhat spherical shape towards the electron cloud, like seen below in this diagram, with all of the electrons being roughly symmetrically distributed around the nucleus. On the other hand, there is a small chance that the electrons will be significantly skewed towards one side of the atom, simply due to probability. So if we go ahead and move to the right here, we'll see that the electron cloud could instead look like this. And this probabilistic skewing leads to an asymmetric electron cloud with a significant excess of electrons on one side of the molecule and a relatively exposed nucleus on the other side. This skewing matters because it creates partial electric charges on the sides of the molecule. Typically, when the electron cloud is symmetrically distributed, it is uniformly negative all around, and the positive charge of the nucleus almost perfectly cancels out the electron charge to make the atom appear electrically neutral to passerby molecules. So, a symmetrically distributed electron cloud has no partial charges, because the distance between the electrons and the nucleus is much, much smaller than the distance between distinct molecules. So from an outside perspective, it appears that the electrons in the nucleus are combined into this electrically neutral sphere. However, when the electron cloud is skewed due to probability, what happens is that what is known as a transient dipole develops. The sides of the molecule with the exposed nuclei will develop a partial positive charge, and the side of the molecule with excess electron density develops a partial negative charge. We can see rather clearly from the diagram why this is the case. With the proton on the left contributing a positive charge and no electrons to shield it, a net positive charge is seen by the exterior molecules. On the other hand, the side of the molecule on the right carries a partial negative charge because all of those excess electrons do not have their combined charge completely canceled by the nucleus, since now the nucleus is relatively far away from that source of electron density. It's not completely enveloping the nucleus. Now, this is where the bread and butter is. When a transient dipole that has been created by chance due to simple probabilistic skewing approaches another molecule, it will exert an electrostatic force on that adjacent atom due to its partial charges, which will look something like this. The partial charge on the transient dipole exerts an electric force on the electron cloud of the other molecule and will skew it, by example, repelling its electrons away from the partial negative charge on the transient dipole. And this will create what is known as an induced dipole. So now we've gone from having one skewed dipole molecule to having two skewed dipole molecules, simply from having this transient dipole create an induced dipole in the second atom. Now, once these two polarized species are in proximity, the nearby opposite partial charges will attract one another due to the usual electrostatic Coulomb interaction, right? Opposite charges attract. So if we put these two molecules together, we'll see that the partial negative and partial positive charge that are aligned in the central point is going to pull these molecules together, as indicated by the purple arrows. This attraction pulls together the molecules, leading to a sort of molecular cohesion, or intermolecular force as it's known, which leads the molecules to cluster around each other rather than flying off to infinity due to their thermal energy. This clustering is what makes tangible matter possible, and it's known as a London dispersion force. Sometimes the transient dipole interaction that we're seeing here is also referred to simply as London forces or just dispersion forces, or even as van der Waals forces. It doesn't really matter what you call them. It's this special interaction between the transient dipole and the induced dipole that is the heart of London dispersion forces and the heart of much of intermolecular force chemistry. I cannot stress enough the significance of these forces. It's really not to be underestimated. They are present in any and all compounds. From noble gases like helium to large complex biomolecules, every atom or molecule exhibits some degree of London dispersion forces. They also tend to be the dominant intermolecular force in larger molecules, especially nonpolar substances, where electron clouds can create very powerful transient dipoles. They're also particularly important in governing the behavior of most gases and other nonpolar compounds, which simply lack the ability to interact with any sort of dipole-dipole interactions or other intermolecular force. There are also several distinct molecular properties which we can point to, which influence the strength of London dispersion forces. Namely, the size of the molecule, the size of its electron cloud, its polarizability, and even the shape of the molecule, its molecular geometry. And we'll cover all of these things in great detail in some of our other videos. But for now, let's just appreciate the absolute ubiquity of London dispersion forces and how they arise from something as incredible as the probabilistic skewing of an electron cloud. It's a complete bending of what we would take as classical physics and really pushes us into the quantum world. And with that, we've gone ahead and reached the end of the content for this video. Thank you guys so much for watching, and if you enjoyed what you saw, please like and subscribe to the channel. Also, make sure to check out our other videos on the chemistry playlist to learn more, and if you're looking to branch out, check out our other science playlists as well. See you next time.